Part 4. The Sun, Stars, and Galaxies. Our Sun is a typical star. At approximately 5 billion years old, it is approximately halfway through its projected lifetime. The Sun's stellar classification is as a G2 type main sequence yellow dwarf. The Sun is composed primarily of hydrogen and helium. The Sun, like all stars, shines due to thermonuclear fusion. The main fusion pathway in the Sun is the proton-proton chain reaction. 4 protons fuse to form one helium nucleus, neutrinos, positrons, and energy equal to the difference in mass, in the form of gamma rays. Outward pressure due to the temperature of the reaction counteracts the inward pressure of gravity in an effort to achieve hydrostatic equilibrium. The Sun, like all stars, is structured in several layers. The Sun's core is where thermonuclear fusion takes place. Temperatures in the core range as high as approximately 15.7 million kelvins. The radiative zone is the portion of the Sun from the core to about 0.7 solar radii, where energy is transferred primarily by thermal radiation. Photons are emitted, travel a short distance, and are reabsorbed, then re-emitted. Temperatures range from approximately 2 million kelvins to approximately 7 million kelvins. The convection zone extends from 0.7 solar radii to near the Sun's surface. It is separated from the radiative zone by the tachocline. In this layer, the plasma is not dense enough to transfer heat via thermal radiation, and instead energy transfer occurs via convection, with hot material rising, cooling, and falling back like a boiling pot. Temperature falls from approximately 2 million kelvins to approximately 5,800 kelvins near the surface. The photosphere is the Sun's visible surface, below which the solar plasma becomes opaque to visible light. Photons produced here escape the Sun through the solar atmosphere as sunlight. Above the photosphere, the temperature drops to a minimum of about 4,100 kelvins at about 500 kilometers above the surface. Above this region, the temperature rapidly increases to approximately 20,000 kelvins in a region called the chromosphere, so called because light shining through this part of the solar atmosphere produces the solar emission spectrum. Above the chromosphere is the Sun's corona, a region of diffuse particles streaming out from the Sun in the solar wind. Though the particle density is only around 10 to the negative 15 power to 10 to the negative 16 power grams per centimeters cubed, for unknown reasons, the average energy of each particle is very high, leading to average temperatures in the corona of 1 to 2 million kelvins. The Sun's photosphere is broken up into cells called granules by the convection from below. Dark areas on the photosphere, called sunspots, are places where magnetic activity inhibits convection, leading to a relatively cooler area of the photosphere. The sunspot cycle is the 11-year cycle over which the number of sunspots visible on the Sun's photosphere varies from maximum to minimum and back. The magnetically heated solar atmosphere exhibits a number of different phenomena that release energy in sudden eruptions. Solar flares are sudden bright flashes visible in the Sun's limb, the edge of the visible solar disk. They are associated with large releases of energy. Flares are sometimes accompanied by coronal mass ejection, CMEs, events where a large burst of energetic particles is released from the Sun's corona. Solar prominences are large, bright gaseous features that extend thousands of kilometers from the photosphere. These often appear as a loop, where the electrically charged plasma follows along magnetic field lines. Streams of plasma are released from the upper layers of the solar atmosphere and accelerated outward into the solar system by the Sun's magnetic field. This stream of charged particles is called the solar wind and consists of mostly protons and electrons. This wind, and the flares and CMEs that periodically occur, causes space weather. This weather can cause significant solar storms that damage space and ground-based electrical equipment. This is also what causes the aurora at the Earth's poles. Stars are classified based on their emission spectrum, where each line indicates an element or molecule in the star's makeup, and the equivalent width of each line indicates the element's abundance. The spectral class is assigned to a star based on the star's surface temperature. The system in most common use is the Morgan-Keenan system, which uses the letters O, B, A, F, G, K, and M, from hottest to coolest. Each letter class is further divided into numbers, from 0, the hottest, to 9, the coolest. Plotting the temperature, spectral class of stars versus their luminosity, apparent magnitude, produces the Hertzsprung-Russell diagram, H-R diagram. Natural groupings appear when the stars are plotted on the Hertzsprung-Russell diagram. These are luminosity classes and correspond to the size and brightness of the stars in each group. The majority of stars fall into a path called the main sequence. A Roman numeral is added to the spectral class of a star to denote its luminosity class. Class 0, or 1A+, hypergiants. Class 1, supergiants. Class 2, bright giants. Class 3, giants. Class 4, subgiants. Class 5, dwarfs or main sequence stars. Class SD, or 6, subdwarfs. Class D, or 7, white dwarfs. Our Sun is classified as a G25 star. It is a main sequence star with a surface temperature of around 5,700 kelvins, a so-called yellow dwarf. As discussed when talking about the birth of the solar system, stars are formed from the gravitational collapse of a molecular cloud of gas and dust into a stellar nebula, which forms into a disk due to conservation of angular momentum. A protostar forms at the center of this spinning disk, as gas and dust is concentrated further due to gravity. While the protostar is hot due to the pressure of the infalling gas, it isn't a true star until the pressure is high enough in the core to initiate thermonuclear fusion. Radiation from the thermonuclear reaction counteracts the collapse due to gravity, and hydrostatic equilibrium is reached. Objects that are not quite large enough to start fusing hydrogen, but are still larger and hotter than planets, are called brown dwarfs. Stars often form in groupings from the same clouds of gas called stellar nurseries. The radiation from the new stars eventually causes the remaining gas and dust to disperse, halting stellar formation. Larger stars are more luminous, as they fuse more of their fuel at a given time than smaller, less luminous stars. However, this means that larger, more luminous stars also have shorter lifetimes than smaller stars, as their fuel runs out more quickly. As they go through their lives, stars follow an evolutionary path through the Hertzsprung-Russell diagram, changing spectral class and luminosity. A star like the Sun starts its life on the main sequence path. As hydrogen fuel runs out in the core of the star, fusion ceases there, leaving a core of helium, which shrinks and heats. This then drives hydrogen shell burning in the layers around the helium core. The star actually gets brighter and moves away from the main sequence to the subgiant branch. The increased luminosity causes outer layers to expand greatly, and the star becomes a red giant. As more and more helium falls into the core of the star, the increased pressure causes helium to fuse into carbon in the triple alpha process. 4 helium plus 4 helium translates to 8 beryllium plus energy. 8 beryllium plus 4 helium translates to 12 carbon plus energy. The increase of energy and core temperature does not change the pressure, due to electron degeneracy supporting the core instead of outward thermal pressure. Eventually, thermal pressure takes over, leading to a sudden helium flash. The star's core is now stable and fusing hydrogen, but it is less luminous because the helium flash has expanded and cooled the core. The star enters the horizontal branch of the H-R diagram. When helium burning begins to come to an end, the star again expands and re-enters the giant group on the asymptotic giant branch, now with a core of carbon. Lacking the mass to fuse carbon, a Sun-like star ceases most fusion in its core and cools. The outer layers continue to fuse and expand, cooling and heating in pulses, until the outer layers are ejected entirely, forming a planetary nebula. When a star reaches the end of its life, its fate will depend upon its mass. What remains is called a stellar remnant. A star like the Sun ejects its outer layers as a planetary nebula. What remains is a white dwarf, a small, dense, cooling carbon core. This will be the fate of the Sun at the end of its approximately 10 billion-year lifetime, 5 billion years from now. For larger stars, fusion does not stop at carbon. Heavier elements can continue to fuse in progressive shells around the core. As each element is consumed, the core contracts, heats up, and fuses the next element in the chain. This continues until iron is produced. Fusion of iron atoms into lead would be a net energy loss. Without outward thermal pressure, the core contracts and heats to approximately 10 billion kelvins. This breaks all the atoms in the core into elementary particles, protons, neutrons, and electrons, via photodisintegration. This cools the core, causing it to collapse even faster. Electrons are crushed together with protons to form neutrons and neutrinos. P plus E translates to N plus V. The core now abruptly collapses until the neutrons are in direct contact. This stops the collapse suddenly, and the collapsing gas rebounds from the solid neutron core, exploding the outer layers of the star in a supernova. The released energy not only blows the outer layers of the star outward into a nebula, but also supplies enough energy to cause the fusion of elements beyond iron, a process called stellar nucleosynthesis. This is the source of all elements heavier than iron in the universe, seeding future generations of stars and planets. In addition to the nebula, the core of neutrons is left behind as a dense, hot mass called a neutron star. These stellar remnants have intense magnetic fields and are often powerful radiation sources in the gamma and X-ray ranges. Spinning neutron stars whose beam of radiation periodically sweeps across the Earth are called pulsars. For even more massive stars, those above the Chandra-Sekhar limit, not even the neutron degeneracy pressure, the neutrons not wanting to be in the same space and quantum state, is enough to stop the core collapse. The smallest size reached is unknown. According to general relativity, it could be an infinitely dense singularity. The resultant object is called a black hole because the density is so high that even light is bent on paths that can't escape the singularity. Our galaxy, the Milky Way, is a barred spiral galaxy. It is approximately 100,000 light-years, 30 kiloparsecs, in diameter, and approximately 1,000 light-years, 0.3 kiloparsecs, thick. The mass of the Milky Way is approximately 1.5 trillion solar masses. Most of this mass is dark matter. The Milky Way contains between 200 and 400 billion stars. Seen edge-on, the Milky Way has a distinct large-scale structure. The circular galactic disk, where our solar system lies, swells in the center into a galactic bulge. The disk and bulge are embedded in a roughly spherical ball of older stars called the galactic halo. A circular, flattened region broken up into the relatively bright areas of the spiral arms and alternating with darker, invisible and UV light areas. The spiral arms of the Milky Way and galaxies like it are brighter because that is where most of the new star formation takes place, so newer, more luminous stars are more abundant there. The spiral arms of the Milky Way cannot rotate along with the galaxy, as they would curl up. They must be density waves. This accounts for the star formation, as gas is relatively more dense there, forming molecular clouds that become stellar nurseries. The galactic disk swells in the center to a fatter bulge. Our view of the center of the Milky Way is blocked by gas and dust that is opaque to visible light. It can be imaged in the X-ray and infrared ranges of the EM spectrum, which can pass through the intervening clouds. The galactic center contains hundreds of thousands of closely packed stars around a strong radio source, Sagittarius A starred, which is now known to be a supermassive black hole, 4.1 to 4.5 million times the mass of the Sun. Surrounding the galactic disk and bulge are the stars of the galactic halo of old stars. All the stars are older because no active star formation takes place in the halo. Many of these old stars are tightly packed into globular clusters, orbiting the galactic center. Stars in these clusters are tightly bound by gravity, unlike open clusters of stars in the galactic disk. Orbital velocities of objects, stars, luminous nebula, etc., in the galaxy can be determined from the redshift of known emission lines, like the 21 centimeters emission of neutral hydrogen. Plotting the orbital velocities of visible objects versus their distance from the galactic center produces a rotation curve. If the brightest parts of the galaxy have the most mass, trailing off into the disk, then using Kepler's laws, we might predict that the rotation curve of the Milky Way and other spiral galaxies would be high near the center of the galaxy and trail off to slower orbital velocities farther out. The actual rotation curve of observed spiral galaxies shows that they are flat rotation curves to well outside the visible disk. Therefore, matter in the galaxy is not distributed in a way that matches their visible light output. Some sort of dark matter, as much as 95% of the total galactic mass, exists throughout the galaxy and extends in a dark matter halo far beyond the visible extent of the galactic disk. The Milky Way has several small companion galaxies, the two largest of which are the Small and Large Magellanic Clouds. The Andromeda Galaxy, our nearest neighbor galaxy, is a spiral galaxy, approximately 780 kiloparsecs from the Milky Way. It is thought to be approximately the same mass as the Milky Way, but is wider, about 220,000 light-years in diameter. It is expected to collide with the Milky Way in approximately 4.5 billion years. The Milky Way and the Andromeda Galaxy are part of the Local Group, a group of 50 closely bound galaxies. Galaxies are classified according to their shape. This classification is sometimes arranged in a Hubble tuning fork diagram, invented by astronomer Edwin Hubble in 1926. Elliptical galaxies lie at one end of the diagram. They are smooth, featureless light distributions and are classified from near circular, E0, to mostly flattened, E7. Lenticular galaxies, classified as S0, lie at the point where the diagram branches. They have a bright central bulge surrounded by a disk structure with no arms visible. The spiral galaxies form two parallel branches on the diagram. Spiral galaxies have a flattened disk and central bulge, with the disk arranged in a spiral structure. Half of all spiral galaxies have a bar-like structure, extending from the central bulge which then branches into the spiral arms. These are called barred spiral galaxies. The other spiral galaxies do not have this bar structure and are called regular spiral galaxies, or simply spiral galaxies. Spirals are classified with the letter S, while barred spirals use SB. They range from SA, SBA, for tightly wound spirals, to SD, SBD, for very loose spirals. Irregular galaxies do not fit in the Hubble tuning fork diagram because they lack a definable structure or are asymmetric. They are classified IRR. The luminosity of most normal galaxies ranges from approximately 10 to the 6th power solar luminosities, dwarf galaxies, to approximately 10 to the 12th power solar luminosities for very large elliptical galaxies. As many as 40% of bright galaxies, above 10 to the 10th power solar luminosities, have a luminosity much larger than their size would normally explain and emit radiation in significantly different parts of the EM spectrum than normal galaxies. These are called active galaxies. There are many different types of active galaxies. The source of their emissions is usually in or near their cores, called active galactic nuclei, AGN. Seyfert galaxies are normal spiral galaxies whose nucleus is approximately 10,000 times brighter than the center of the Milky Way. These galaxies emit radiation in a broad spectrum, but it is centered on the IR. Emissions often vary over time, creating pulses. They are thought to be caused by violent non-stellar activity in the core of the galaxy, like matter falling into their central black hole. Radio galaxies are active in the radio portion to the EM spectrum. Energy is not released from the nucleus, but from huge extended regions called radio lobes, about 10 times the size of the Milky Way. They are caused by material thought to be ejected at high velocity from the galactic nuclei. Quasars is short for quasi-stellar radio sources. These are created by material falling into a supermassive black hole of millions or billions of solar masses. They are very luminous, 10 to 10,000 times the luminosity of the Milky Way, but very distant, between 600 million and 29 billion light-years away from the Earth, and receding at a very high redshift, meaning that they were more common in the early universe. Stellar parallax can be used to measure relatively close objects, like nearby stars, but it is impractical for larger distances. The apparent brightness of objects of known luminosity, called standard candles, are measured to construct a distance ladder. Variable stars, which vary in luminosity over a fixed period, are used as standard candles. RR Lyrae variables are low-mass stars on the horizontal branch of the Hertzsprung-Russell diagram that have evolved off the main sequence and are unstable, pulsing their luminosity as the core cools and shrinks. They all have approximately the same luminosity, which can be immediately known once they are recognized. Cepheid variables are high-mass stars in the unstable portion of the horizontal branch of the H-R diagram. Their pulsation can be directly correlated to their luminosity, known as the period-luminosity relationship. For longer distances, Type 1 supernovae are used as standard candles. All of this type of supernovae are known to have nearly the same luminosity. Active galactic nuclei can extend the distance ladder even farther, though the values for their luminosities are less well known. The local group is a bound group of about 50 galaxies, including the Milky Way and the Andromeda Galaxy, surrounded by the local void. It has a diameter of approximately 3 megaparsecs. The local group is, in turn, part of the Virgo supercluster of galaxies, consisting of at least 100 galaxy groups and clusters in a 33 megaparsec diameter space. In turn, the Virgo supercluster is part of an even larger supercluster, the Laniakea supercluster, which is centered on a gravitational anomaly called the Great Attractor. The largest scale structures in the universe are galactic filaments, galactic walls, and galactic sheets. These form a foam-like structure around vast empty spaces called cosmic voids. In the 1920s, Edwin Hubble and colleagues discovered that the emission and absorption spectra of galaxies that they were observing was always redshifted, meaning they were moving away from us, and that more distant galaxies were more redshifted. Hubble's law states, the velocity at which a galaxy is moving away from us is proportional to the distance to that galaxy, or VR equals h0 times dg, where VR is the recessional velocity, dg is the distance to the galaxy, and h0 is the Hubble constant. Hubble's law would be true no matter where we are in the universe, because space is expanding, carrying everything away from everything else, like points marked on a balloon as it is blown up. The Hubble constant is the rate of that expansion. This implies that the universe expanded from something, and that, rather than existing in a steady state forever and continuing forever, the universe had a starting point, the Big Bang. The Big Bang is defined as when an infinitely dense singularity exploded, releasing all the energy in the universe. For a brief time after the Big Bang, 10 to the negative 35th power to 10 to the negative 33rd power seconds, the new universe expanded much faster than the speed of light, and, for reasons not yet totally understood, increased more than 1,030 times in size, a process called inflation. This explains two problems: the flatness problem, which states that the universe is too flat; the uniformity problem, which states that the cosmic microwave background radiation is too smooth. After the Big Bang, the expanded universe cooled until particles could form. Electron-positron annihilation left some electrons behind, leading to the existence of matter instead of antimatter in the modern universe. Protons and neutrons formed the first atomic nuclei, predominantly hydrogen, with some helium. Around 377,000 years after the Big Bang, the universe cooled enough for electrons to be captured by nuclei, meaning that photons could now travel long distances without immediately being reabsorbed and re-emitted. At this point, the universe was transparent to radiation. This surface of last scattering is the earliest visible part of the universe, and the radiation from this surface, now redshifted to the microwave portion of the EM spectrum, forms the cosmic microwave background, CMB radiation. Measurements of the CMB can be used to pinpoint the age of the universe at 13.8 billion years. Formation of the first stars and galaxies took place about 150 million to 1 billion years after the Big Bang. Beginning about 9.8 billion years after the Big Bang, the expansion of the universe stopped decelerating due to gravity and began to accelerate. This accelerating expansion of the universe does not have a precise known cause. Some unknown form of dark energy is counteracting the gravity of the normal mass energy of the universe, causing it to expand at an increasing pace. The fate of the universe depends on what its average mass energy density is in relation to the critical density needed to slow, stop, and reverse the accelerating expansion of the universe. There are three possible shapes for the space-time of our universe: the flat universe, which means that space is infinite and has a flat geometry; the open universe, which means that space is infinite and has a curved geometry; and the closed universe, which means that space is finite and closes back on itself with a curved geometry. There are three possible fates of the universe. The first is the Big Rip. This would be caused by gravity that is too weak to stop the expansion of the universe, causing it to expand at an increasing rate forever, leading to a big rip. The next is the Big Crunch. This would be caused by gravity stopping the accelerating expansion of the universe, causing it to collapse into a big crunch. Finally, there is a theory of the heat death of the universe. This means that expansion will slow but never stop. Eventually, all matter and energy in the universe is distributed evenly over an infinite space, leading to the heat death of the universe. Current observations show that the universe is very flat, meaning that neither a big crunch nor a big rip seem likely to happen. Current best measurements indicate that the energy and mass in the present-day universe is divided into 68% dark energy, 27% dark matter, and 5% normal matter. The rotational curves of observed galaxies require that more matter be present than is observable as luminous, normal matter. This dark matter is not simply normal matter that is not emitting radiation. It must be some sort of unknown form of matter that exhibits the following properties. First, it does not interact with electromagnetic radiation, and thus is invisible. It only very weakly interacts with normal matter. Next, observational evidence of dark matter beyond the rotation curves of galaxies includes both gravitational lensing by non-visible mass in observations of background galaxies, as well as the bullet cluster, a collision between two galaxies where the observed center of mass is far removed from the center of the visible normal mass. Dark energy is the unknown form of energy that is hypothesized to permeate all of space, accelerating the expansion of the universe. Other than the observation that something is causing the expansion to accelerate, little is known about the underlying cause of the acceleration. The effects of dark energy might be constant, the cosmological constant, or might vary over time and space. Any variation might be very subtle or very slow, and thus difficult to observe. Research is ongoing on this topic. This concludes Peterson's DSST astronomy instructional videos. Good luck on your DSST exam!